Okay, let's dive into this. Have you ever stood in front of some massive skyscraper or honestly even just walked around a typical residential house and wondered what on earth is actually happening in the dirt right below it? We almost always look at buildings as these static, completely solid objects just resting peacefully on the ground. But the crazy truth is, beneath literally every structure, there's this complex, totally invisible physics dance happening at all times. Welcome to this explainer. Today we're going to map out exactly how buildings negotiate with the earth beneath them.
To really grasp this hidden world, we're going to break it down systematically. First up, the hidden foundation dance, just to get the core rules down. Number 2, clay, which we're calling the elastic bowl. 3, sand, or the escaping edges. And finally, number 4, real-world engineering reality.
All right, Section 1, the hidden foundation dance. To get started here, we actually need to shatter some very basic, everyday assumptions about how buildings interact with the ground.
So think about this for a second. If a building pushes down evenly, does the ground sink evenly? I mean, intuition tells us that if you have a perfectly flat, super heavy structure, it should just push the ground straight down in a perfectly uniform way, right? Kind of like pushing a flat block into a soft kitchen sponge. Well, in the wild world of soil mechanics, it is actually rarely that simple.
Here is the thing. Whenever a foundation rests on soil and carries a uniform load, you don't just get independent reactions. There are exactly two linked phenomena that always happen together. You literally cannot separate them. They are in this constant, dynamic relationship, constantly negotiating exactly how the building is going to settle into the earth.
So the absolutely crucial point here is understanding the first of these two phenomena. It's called contact pressure distribution. Now, this isn't the weight of the building itself, okay? It's how that pressure is actually distributed across the base of the foundation, right where it meets the dirt. If you were to imagine drawing arrows pointing straight up from the soil into the foundation, this dictates exactly how long and where those arrows are. And as you'll see in a minute, those arrows are rarely all the same size.
Right, so the second phenomenon is the settlement profile. This is the actual physical shape the ground surface takes after it settles under all that weight. Just imagine a curved line showing the exact dip in the earth. Now here is the absolute secret to everything we're going to discuss today. These two things, contact pressure and settlement profile, they are inextricably linked. The shape of one depends entirely on the other. But, and this is a big but, it also depends on two massive variables: whether the foundation itself is flexible or rigid, and whether the soil you're building on is clay or sand.
Moving on to Section 2, clay, the elastic bowl. Let's see exactly what happens when we place our foundation on cohesive soils, which, as it turns out, act a whole lot like an elastic bowl.
Notice the incredible contrast here when you look at flexible versus rigid foundations on clay. If you have a flexible foundation, it actually applies the contact pressure uniformly. You get equal arrows all the way across the width. But because it's flexible, it basically just conforms to whatever the soil wants to do. It can't force the ground to stay flat. So what happens? It sags. You get the largest settlement right there in the middle, and much smaller dips out at the edges. But now look at the rigid foundation. A rigid foundation absolutely forces a uniform flat settlement across its entire base. It won't bend. So to achieve that completely flat settlement in clay, the ground has to push back differently. The contact pressure must be way higher at the edges and lower in the middle. This creates this really distinct dish or saddle-shaped pressure distribution.
So why does clay behave this way? Well, as the source material notes, quote, because clay deforms elastically in a bowl-like manner, end quote. When you press down on clay, it actually has more confinement and much higher shear resistance right near the edges. Because those outer edges are tough and really confined, a rigid foundation has to exert way more pressure there just to force them down to the exact same flat level as the softer yielding middle. Honestly, it's a bit like trying to flatten out a really stubborn ball of pizza dough. The edges fight back the hardest.
Okay, so we know clay fights back at the edges, but what if the ground isn't sticky, cohesive clay? What if instead we build on loose, granular sand? Take a second to guess how that might change the physics.
This brings us to Section 3, sand, the escaping edges. We're moving over to cohesionless soil now, where the foundational rules pretty much completely flip upside down.
Let's look at the exact same comparison we just did, but now we're in sand. If we use a flexible foundation, it applies that uniform pressure again, but the settlement profile, it is totally different. The largest settlement is out at the edges, and the smallest is in the middle. The edges literally drop away. Now look at the rigid foundation in sand. Just like before, a rigid foundation forces a totally flat settlement. But to actually achieve that flat profile in sand, the contact pressure needs to be higher in the middle and much lower at the edges. This creates a parabolic or dome-shaped pressure distribution, and this brilliantly illustrates the absolutely wild reality of soil mechanics. Sand has the exact opposite curvature of clay. No way, right? Where a rigid foundation on clay experiences a dish-shaped pressure, higher at the edges, well, a rigid foundation on sand experiences a dome-shaped pressure, which is highest right in the middle. It is a complete 180-degree mirror image of physical behavior. So, what's going on here? The reason for this really drastic reversal comes down to the fundamental nature of sand itself. Sand is cohesionless, it's granular. Near the edge of the loaded area, sand has way less confinement. There is simply less overburden resistance from the sides to actually hold it in place. So when pressure is applied, the sand at the edges simply tries to escape. It deforms and weakens laterally. Therefore, if a rigid foundation wants to stay perfectly flat, it actually has to reduce the pressure at these weaker edges. Otherwise, the edges would just sink away entirely.
Which leads us nicely to Section 4, Real-World Engineering Reality. Let's take this highly theoretical matrix we've been building and bring it straight back into practical, everyday reality.
Let's look at how this builds a complete picture. Think back to the top row, which was clay. If the foundation is flexible, you get a sagging profile. If it's rigid, you get a dish-shaped pressure pushing back. Now the bottom row, sand. If it's flexible, the edges drop away. If it's rigid, you get a dome-shaped pressure with all that stress concentrated right in the center. This matrix right here is the absolute fundamental key to understanding how different soils handle the massive weights we put on top of them.
But you might be wondering, why does this highly theoretical matrix matter when you're actually out there pouring concrete? Well, because in practice, real foundations, like standard footings or those massive concrete mats, they are neither perfectly flexible nor perfectly rigid. They exist somewhere in the messy in-between. Engineers use these idealized models because they explain exactly why contact pressure is almost never truly uniform, even when a building looks perfectly symmetrical to us. Assuming uniform pressure is often used in simplified design, sure, but it is ultimately just an approximation. Different stress, strain, and confinement characteristics completely change the hidden physics happening beneath the floorboards.
Which leaves us with this final thought. Every single time you step into a building, there is an active, ongoing negotiation happening between the structure and the earth itself. Based on this hidden dance of pressure and soil, what invisible forces are shifting beneath your own home right now? Is it resting on an elastic bowl of clay, or maybe the escaping edges of sand? The ground is never just dirt. It's a highly dynamic partner in literally everything we build. Thank you so much for joining me for this explainer, and keep questioning what lies beneath the surface.